a lot. It's really observational. So like, we're going to make observations all the way along to kind of figure out what the geology is like. The first one is, this is the oldest rock unit right here. This is the Green Valley tonalite. It's really kind of more like a granite, very similar to a granite. It's phaneritic. I don't know if you remember what phaneritic means. Phaneritic means it's coarse-grained. You can see the grains with the naked eye. In other words, if I pick it up and pull it like this, you'll be able to see the grains, big coarse grains. That means it cooled slowly within the earth. These were the core to the mountains, basically. It's about 100 million years old, somewhere in there. So that's the oldest unit that we see. The one thing that I want you to notice about it, it's, see how the rocks are kind of rounded? So you get joints, you get cracks like at 90 degrees, and they form these kind of onion-looking things. It's called spheroidal weathering. Don't ask me to spell it. It's spheroidal, okay? And it's like when you're going up 15 and you see all the rocks that are kind of just sitting out like a pumpkin patch, onion patch or whatever, they're just sitting on the ground. It's the same exact thing. Okay? So these rocks are mainly comprised of quartz and case bar. Okay, or quartz and feldspar. Let's just say quartz and feldspar. There's a whole bunch of different feldspars. The type of feldspar that's in here is case bar, and it's kind of a salmon color. Okay, it weathers out very, very quickly when it gets broken down. The quartz remains. So you're going to see these reds and oranges in the soil and in different outcrops, and you're going to see things that are spheres in the outcrop, and that'll help you identify that as we get farther along. When we're walking along the road up here, you'll see color changes in the soil as you go, and you can tell when we're going into this rock unit. Okay? Now, to contrast that, see the white stuff way across the way there on the trail? That's the Santiago Formation. That's about 40 million years old. It was deposited as a beach sand. It's sand, and it has a lot of clay in it too, and it has a lot of slumping. So in North County, if you're having slumping, it's probably in the Santiago Formation. Okay, that one's about 40 million years old. It's very soft, so you get low relief from it. You can see it's very, very low. It sits low, anyways. It's very soft. All right, so we're going to go up and just what observations that we've seen here, we're going to start to put these things together. So it's kind of going to look like this right here. This is the Green Valley tonalite here. This is the Santiago Formation. And then this stuff is an andesite or a dacite. Okay? It's a mix of basically oceanic crust and continental crust. This stuff looks like a Dalmatian. Oceanic crust is black, like a black lab. This stuff looks like a greyhound. It's gray. It doesn't look like, it's really punky looking. It just looks like nothing. But it's a volcanic rock. You can't see any grains in it. So as we're walking up, we're going to stop and we'll look and see if we can figure out what is what. Okay? So let's go up. See crystals in there, right here?
Yeah.
You do see crystals.
Right here.
You might find an isolated piece.
Well, there's a white vein through it. It looks like a white vein.
Let me see. You can just throw it. Throw it at me. Yeah, this is just it's too weathered to really tell. But look at this right here. How about this one?
No. Not from here, I don't.
So what do you think that might be?
Well, that's volcanic stuff you're talking about?
That's volcanic stuff, okay? Here is what this tonalite looks like in places, okay? Here, this is it. So you can see the grains right here? See the texture? So this cooled slowly at depth. This was erupted out of a volcano, okay?
What? Because it doesn't have the different veins in it?
The different crystals. So this is, to get crystals, it has to cool slowly generally, okay?
So that just oozed out, and that was kind
This
of
one came straight to the surface in violet eruption. Yeah. Okay, so let's come on up. or 25 million years ago, we had subduction. Do you guys remember what subduction is? Take oceanic crust, the black lava rocks, push it down, it melts, it comes up through the continental crust, and on top you get andesite volcanoes, just landward side of the, of this subduction zone of the trench. Okay, that was up to about 25 million years ago. And then you notice we start subducting spreading centers. Do you remember what spreading centers are? Oceanic crust pulling apart. This opens up windows. I would say it opens up a window of soul from the bowels of the earth, right? Because it's like a zone of weakness where the stuff can come up, right? Well, that's the subduction process. This is how you get andesite volcanoes, okay? The big andesite volcanoes. This andesite volcano is like the most puny one you'll ever see in your whole life, okay? I mean, I'd like to stand here and say, oh, this is a really big explosion. No, it's like, this thing's puny. So here's what we're looking like, what it looks like now. Here's the Pacific Plate, North American Plate. There's a subduction zone up here, andesite volcanoes, right? They're active. We have the San Andreas Fault that comes across like this, and then we have a spreading center in the Gulf of Mexico. All right, so that's what it looks like right now. So we don't have subduction here now. But what we think happened here is a couple things, is that you get, this is about 20 million years ago, okay? So the Santiago is 40 million years, Santiago Formation. All right, the tonalite's about 100 million years old. So what happened is this stuff was getting subducted. They think that you were flexing the leading edge of the continent here. And you're also, there's another thing that could happen, is you have this spreading cinder here that's a zone of weakness, and it's going underneath this crust, this continental crust, right, which is like the tonalite, basically. Then you mix this with that, and you get the andesite or dacite, same, interchangeable for us. Okay, so what happens is you get these little volcanic plugs. So we have volcanic plugs that are not where the actual andesite, big andesite volcanoes were. Those were back by Escondido. Okay, those were the big ones where they had like the oceanic crust melting, lots of volumes of stuff coming up. Here, there's just like a little burp kind of. Okay. But they're all the way from Mexico, all the way up into LA. They have these little plugs. There's another one up on Pendleton. Can't remember the name of it. But anyways, all along the coast. These little plugs like that. So they're andesite, but they're not like the really true, like, explosive andesite that's gonna blow up and kill you. All right. A couple things that we're gonna do is that we're gonna figure out the relative ages of the rocks. This hasn't been age dated. Okay. It's only done from relative age dating. One rock is older than this. One rock is older, this rock is younger. And there's a series of logic. So the logic we're going to use is superposition. Is the first one. That just means A is older than B, right? So you can't just cram A underneath B and call it good. I mean, A has to be there, then you get B. Huh? Makes sense? The next one is called cross-cutting relationships. This is what we're going to see here. It could be a fault, or it could be a dike, or it could be an intrusion. So what it means is A and B is sitting there, and then something cuts through it. It could be a volcanic plug coming up through it, a fault, whatever. It just means that this feature is younger. Okay. The third one that we're going to see, well, we are going to see this, but we could have if we were here about 8 years ago, because it's gone now. But I'll show you where it is. There are these things called inclusions. So when this volcano erupts, it's kind of like it's like volcano vomit. Okay, it just comes up, rips up all the rocks around it. And it has big chunks in it, like if you threw up and you ate carrots or something like that. What it does is, when this dacite plug came up through this tonalite, it rips up pieces and puts it in here. There's an inclusion, and so that means the inclusions are older than the other rocks. Okay, we're going to use those 3 observations. We've already done that. Okay, now we get to actually look at the geology. Right, so this is going to be interesting. I'm going to stand up in front of it. You can almost imagine, see the really dark gray stuff right where the guy's about ready to fall. Yeah, all the way around to here. You can see kind of the gray stuff, and you can see those fingers coming up. You can almost imagine like being flow lines. Dark gray stuff are this volcanic plug right here. On this side. See where you see the volcanic dark gray stuff? And all of a sudden you go to the left, and it's white. And right, there's a little sliver in there where it like looks a little bit dark. So it's kind of thrown out over it and exploded. You'll see up here, right there, to the right, you can see to the left of that big tree is a dark gray. That is the volcanic plug, okay? To the right of it, and you can't see it from here, you can see a little piece of it. Way to the right, you see that it's white, and it's soft. Move up closer to the day site, and you can see staining, like reddish staining or darker staining. Those are baked zones. So this stuff comes out at like, and it bakes the rocks next to it, alright? This is the observation that told them that this plug had to be younger than the Santiago Formation. That's Santiago and that's Santiago Formation. They mapped this in the 40s. So do you remember how old the Santiago Formation is?
40.
Yeah, so is it younger or older? It has to be younger, yeah. So we're making a series of observations. We're trying to figure out the relative ages of these things. If we don't, like we didn't know any dates at all, basically. So what we're going to do is we're going to walk up this way. I'm going to stop. There's 1, 2, maybe 3 little stops. Santiago Formation is 40 million years old. You can see the gray stuff coming over the top of it. Very weathered. That is probably a volcanic unit that's weathered into a volcanic soil. Okay. The main reason that I wanted to stop and have you look at this is to notice what the color of this is. This material on the ground. It's going to change color as you walk up there, and that means if it's changing color, that something's happening, right? Okay, probably changing the geology. So as we come up, go up this way, we'll look at it, and when you see the changes, I'll try and point it out a little bit, okay? Hopefully we can see it. It's kind of dry, but I don't know, we should be able to see it.
It's orangish up there.
Yeah. Do you remember what is orangish?
Iron.
Fake stuff.
Not the fake stuff. The feldspars, yeah. So now we're going to cross into weathered Green Valley tonalite. And you can see it from here, and you can see that. Can you guys see this up here? No, they like to play. So anyways, yeah. We're just making like simple observations. I'm going to just ask you some questions, okay? Can you see grains in that? For sure, right? Do you see circles?
Yeah.
See the circles like right here? Circles, right? And what color is it?
Orange.
So that is weathered tonalite. Remember how it looked like?
Raw sienna.
Yeah, it looked like dark and really like heavy, yeah. And then it weathers out. What it is this feldspar weathers out very quickly. Has anybody been up here when after it's rained? This stuff is, you can barely walk on it. It's so slippery. It's the clays and the feldspar. It's doing that. So, this brings us to the point of why we have so much sand on the beach. What is the sand made of on the beach?
Granite.
This.
That's what it's sourced from, but what is in the sand?
Silica.
Someone said it.
A feldspar
I heard it over there.
and a lot of quartz. The reason that we have so much quartz and sand on the beach is that when the rocks, the granites weather out here, the feldspars weather out very quickly and leaves the quartz, okay? And it just leaves the quartz, so the quartz travels down here, gets a little bit more rounded as it comes, gets deposited on the beach. Okay? Then when you pick up the sand, you'll see some little pieces of feldspar. They're usually that kind of grayish in color. And you'll see some sparkles, that might be mica, but it's mostly quartz because quartz is the most durable part of it. Okay, the feldspars weather out really fast. So, all right. So, anyways, oh, and then one other thing is when you start looking up above this, what do you start to see? What's this stuff look like? See, look at this contact right here. Look right up in here. What's this?
Volcanic erosion.
It's dirt. Yeah. It's probably the volcanic unit that's weathered. Because when we go around the corner, it doesn't take very much imagination to see a lava flow come in over the top of the tonalite. Okay. So we're gonna go over there and look at that. Hey.
That's the weather tunnel light.
Yes. Yeah.
Top.
So the idea is to figure out the characteristics of the fresh samples and see how they weather, so you can identify them in weird places like this, right? Just a little simple observation. Reddish pink. So what is it? Weather tonalite, right? I'm standing on that stuff. You can't see it here, but they plug this additive, and below it, on the edges, you can see some of the tonalite. So the tonalite is underlaying this. This right here is probably a lava flow, or maybe even a mud flow, or just a weathered lava. But you can see chunks up in here. You can see pieces of the dacite, chunks of it, volcano vomit, chunks, you know, like throwing up carrots. Those are the carrots right there. So why did they dig here? So here's why they dug here. They realized that these are volcanic rocks, and are volcanic rocks warm or cold? They're warm. Things that are warm can hold more minerals. Hold more minerals in water. They can be more dissolved minerals. So when it cools, they precipitate out. Just like a cloud coming through. A cloud comes through, and what happens when it supersaturates and hits 100% humidity? Let's say you take a warm air and then you cool it off. The warm air can hold all this fluid, but then you cool it off. What happens? It rains. So this is like the same thing you have. So these miners, whoever came here to do this, they recognized that they had these lavas coming over the top of the cool tonalite. So they dug a hole in there to see if there were minerals in that interface. Okay, and they just plugged this. It hasn't been. I mean, it's only probably been 6 months or so. This is probably some little rubble from the tonalite, but it doesn't take very much of an imagination to see where the fence is, see where the gray stuff comes across, how it's kind of flowing. You can almost imagine that being a lava flow coming across. Especially when you see the pyroclastics near the bottom. What does that mean? It blew up first, and then the lava flow came over the top. Okay? So you can see that. It's pretty interesting. You can see little pieces of the tonalite over here to your left, kind of. Little windows. Hey, Sarah, or Roberta. Fenestras? In Spanish.
Yeah, fenestras.
Yeah, it's like a
window.
It's a German term, yeah, for window. It's like seeing a window in that. What's that?
I think it's Latin too.
Oh, is it? Probably German, Latin.
Fenestrate, I think it is.
German Latin is not the same.
So anyways, so you can see the lava flow coming down the bottom of the pyroclastics. So that this dacite weathers very quickly, and that's why it's kind of brownish, grayish, mucky stuff. Then if you look up here, you can see it from here. See that outcrop up there? That's more of the less weathered dacite, I think. This stuff is probably thicker there. This is probably thinner, so it's easier to weather, like water can go through it and all that stuff and, you know, break it down and all those things. But up there it's probably a little bit thicker. Okay? So we'll go up here, we'll cut over to the left, and then we're going to go down there, and that's the last stop, okay? Notice? What different colors are you seeing in here?
Yellow and red.
This is common name, you know?
I'm not hearing the one I'm looking for, but
Seeing some white in there.
red, orange,
Greenish.
purple.
Yes,
So like if you look around, you start looking around here as you walk down, you'll start seeing a lot of kind of purples and reds and stuff. Some of it will be like pieces that are all purple. Those are these colors like that are very diagnostic of hydrothermal fluids.
this yet?
So what's a hydrothermal fluid?
Hot water.
Hydro is hot water. It's hot water, yeah. So they come through. So this is really common, like in volcanic areas where you have volcanic rocks coming up, and you're seeing these types of colors. If you've ever been to Death Valley, you see a whole bunch of this stuff. Or even out in Anteborrego around like Agua Caliente, you'll see a lot of different colors like that. And as we walk down here, we're just going to walk another 100 feet or so, and just kind of look around and see if you can find places where it's really purple, or see if you can find chunks. I have like a chunk in my house that's just altered. And then, you can see it's altered from the hydrothermal stuff going through.
These lines right here.
The
reason that's they're doing that is
it could be where it's flowing through, yeah. You could get something like that. But the reason we came here is that this rock right there used to be up there. And one of the people that I work with, one of the geologists, he walked around here for like 2 days trying to find an inclusion of the tonalite in the dayside. And there was an inclusion right there. There's a picture of it on my website.
I've seen it.
It's about this big and it's perfect.
It is perfect.
You can tell it's all dayside around it, and you find one inclusion of the tonalite. So what does that tell you about the age of the tonalite? So what does that tell you about the age of the tonalite, which would be this stuff, versus this matrix, which is the volcanic stuff? Yeah. So what we've seen superposition that says that the tonalite is older than the volcanic fluid, right? Yeah. Up here we saw that. Cross-cutting relationships, we know that the dayside cuts the Santiago formation. Okay? So what does that tell us? The dayside is younger than the Santiago formation. And again here we see tonalite and daysite giving you a date. So now, what's the relative ages of it? Relative just means relative to one another. We know that tonalite's the oldest, right? Then we have Santiago, right? This is Santiago. And then we have the volcanic unit. And it's just using these techniques right here. But the thing is the logic you use in geology is a lot different than a lot of sciences. So like, if you're in a chemistry lab and you take chemical A, mix it with chemical B, what happens? You get C. If you do it again 3,000 times, you're going to get the same result. Geology, if a fault moved 60 million years ago, it may not ever move again, but we can't wait 60 million more years to see it would. You could, maybe after you had a number of so anyways, we use a series of logic like this. Yeah.
So the green stuff on this on your board.
Yeah.
Oh yeah. So this is the oldest.
That's the tonalite, yeah.
So this is the newest stuff.
Yeah. So what it is?
Stuff's coming around.
No. So what it's doing is it's volcano vomit. It's like it is throwing up out of the volcanic throat. It is just doing that. It's ripping up chunks of existing rock on the sides.
That's a good visual right there for you, actually, on the first one. On the other side, yeah, volcano coming up.
So all it's doing is ripping this stuff up. This is pretty hard usually, especially in depth. Okay, this stuff is really potent. You're never gonna see that probably. But yeah, you're just ripping up pieces of that, and it's coming out like this, and it glows like that. Okay.
So that's not enough to melt the tonalite.
Yeah. Probably not. I mean, this stuff should be hotter than that, but it's very common that when it erupts, it's going to cool fast. But you typically don't see a lot of melting of these types of rocks. These are about 700 degrees melting temperature, and these are probably 11 or 1200, something like that.
So it doesn't have time to
Celsius, yeah, Celsius. But for some reason, you don't see these getting incorporated into it, or they completely melt. And you don't see them. But you do see places where it's preserved. You see them, it's very distinct. So if you go on my website, on the virtual labs, look up the Igneous Lab, all the things that we saw today are on there. And you can see the inclusion and all that stuff. Okay? Alright, so that's about it. Do you guys have any questions at all?